Hello, everyone, I am Gaopeng. Today, I will introduce our paper. I have divided presentation into 4 parts: introduction, system description, experimental result, and conclusions. First part, introduction. This paper describes TAL system for the INTERSPEECH 2021 Shared Task on automatic speech recognition for non-native children's speech. In this work, we attempt to apply the self-supervised approach to non-native German children's ASR. Despite the most recent research indicates that the automatic speech recognition system of adult speech can reach the level close to human beings, it is still facing many challenges for non-native children's ASR. The ASR performance will be significantly degraded by some extraordinary phenomena in non-native children's speech, including mispronounced words, grammatical errors, unsmooth words and code switch words. Non-native children's ASR can be challenging due to language differences, physiological differences, and cognitive differences. In addition, due to the lack of a public dataset of non-native children's speech, it is more challenging to develop an ASR system for this field. In order to promote the research of ASR technology for non-native children, INTERSPEECH 2021 proposes a task of the INTERSPEECH 2021 Shared Task on automatic speech recognition for non-native children's speech. The shared task organizers distributed a series of datasets including English and German for non-native children's speech. Datasets are generated in the context of English and German proficiency examinations. For baseline, a CALD system was provided as a German ASR baseline. The baseline ASR system used TLT 2017 and TLT 1618 to train the acoustic model. Firstly, GMM acoustic model was trained using the TLT 2017 train. TDNNF models based on the labels aligned by GMM was trained using TLT 2017 with 3-way speed perturbation. The input features of the TDNNF model were 40-dimension MFCC and 100-dimension I vectors. The model consists of 13 TDNNF layers, and the context of the model is 29 frames before and after the underlying frame. An N-gram language model was trained on the 2016 and 2018 campaign's written answers. Then, this preliminary model was used to create alignments for the TLT 1618. The final TDNNF model was trained with a weighted combination of supervised and unsupervised data, and the procedure follows the recipe proposed in the CALD recipe. The 2 parts training data set provided in the German track, the TLT 2017 and the TLT 1618. The TLT 2017 contains about 4.69 hours manually transcribed, coming from 2017 German TLT evaluation campaigns recordings. The TLT 1618 contains 63.91 hours of untranscribed data coming from 2016 and 2018 recordings. In addition, the TLT 2017 containing about 1.11 hours coming from 2017 recordings was provided as dev set. The TLT 2017 was provided as interval set. Data statistics, such as audio duration, the number of utterances, are presented in table. The ages range of speakers in the dataset is from 9 to 16 years, belonging to different school grade levels. The speakers are divided into 3 age-based groups. Each age group is asked to answer questions according to their language skills. Second part, system description. For data augmentation, to increase the amount of training data and enhance the robustness of the model against different speaking styles, reverberation, and background noises, we applied 7 types of data augmentation methods, namely speed perturbation, volume perturbation, reverberation simulation, babble noise augmentation, music noise augmentation, non-speech noise augmentation, and pitch augmentation. These types of data augmentation, in total, resulted in an 11-fold increase for the training data. For data cleanup, we observed that the original manual transcriptions were provided with symbols representing speech and non-speech noise events, such as laughter and noise, but the transcriptions were not wholly accurate. For example, some audio duration is about 30 seconds, but the annotation result is only one word, and a little audio contains only noise or silence that is not friendly for training acoustic models. In addition, some of the original audio is longer than 100 seconds, which affects the efficiency of using GPU to train the model. We train a chain-based model to resegment and clean up training data, selecting the good audio that matches the transcripts. We decode the original data with a pre-training and domain chain-based acoustic model and a biased language model built from the reference transcript, and then obtain the segmentation from a CTM-like file. We get about 2.6 hours of resegment data, and the maximum length of the audio clip is 30 seconds. Because the amount of training data is relatively small, we finally combined the data less than 50 seconds in the original data with the data after cleanup to get about 6.7 hours of supervised training data. For VAD model, we used the semi-supervised voice activity detection VAD model to segment the original audio. We decoded untranscribed audio with an existing and domain chain model mentioned. VAD targets were obtained by decoding. The phones in the lattices were mapped to 0, 1, and 2, representing silence, speech, and garbage classes, respectively. These targets were used to train a 4-layer TDNN network for VAD. For the pre-training model, an unsupervised training WAV2VEC encoder was used. It consists of a feature encoder, context network, and quantization module. We performed experiments with base model and large model, which used the same encoder, but differ in the transformer block. The base model feature encoder contains 7 convolutions blocks. The number of output channels is 512. Context network contains 12 transformer blocks, each block with 512 dimension model, 8 attention heads, and 2048 dimension feed-forward inner layer. The large model contains 20 layers of transformer block with 16 heads, and the hidden dimension is 1024, and the final dimension is 4096. Trained the baseline model on 8 number of V100 GPUs. The model was optimized with Adam. For fine-tuning, we use a total of 35 tokens, including 30 German characters, a word boundary token, and 4 non-linguistic sharing symbols. Models are optimized by minimizing CTC loss, and we also apply masking to time steps and channels during fine-tuning, which reduces overfitting and improve the recognition robustness like spec augment. We fine-tuned on the transcribed data TLT 2017 with pre-training model and added a randomly initialized output layer on top of the transformer to predict characters. The model was optimized with Adam, and the learning rate was warmed up for the first 1,000 of steps. We fine-tuned on 8 number of V100 GPUs. For the first 1,000 updates, only the final output classifier was trained, after which the transformer block was also trained. The feature encoder was frozen during fine-tuning training. Third part, experimental result. Table shows the results of different models starting from the baseline model to the best performance model. Model 1 shows the improvement gained by 11-fold data augmentation. A 10.5% decrease in the WER was achieved by increasing the transcribed training data augmentation. Model 2 shows the improvement gained by increasing the transcribed training data to around 51.6 hours and untranscribed training data to around 704 hours using 11-fold data augmentation. A 11.4% decrease in the WER was achieved by increasing both transcribed and untranscribed training data. We checked the data provided by the challenge organizers and found that some transcribed were not completely accurate. We resegment and clean up transcribed data. Then, we combined the data shorter than 50 seconds in the original data with the data after cleanup to get about 6.7 hours of transcribed training data. In Model 3, we also used 11-fold data augmentation for 6.7 hours of combined data, and the WER dropped from 34.1% to 30.5%. In Model 4, we used the VAD model to segment the original untranscribed audio, and the duration is from 64 hours to 42 hours. To ensure that there are enough available pre-training data, we combined the original segments and the segments to the VAD model to obtain 106 hours of data, and used 11-fold data augmentation to obtain around 1166 hours data. The Model 5 is like Model 4, but uses large model instead of base model for pre-training, and the WER dropped from 29.6% to 28.2%. 2 n-grams LM were used in our system. A 4-gram LM trained by the TLT 2017 transcripts and a 4-gram LM trained by transcribing the DETLT 1618 with the chain-based model. During decoding, we used a certain confidence threshold to remove some bad results. We linearly interpolated these models, trained on different text, which was improved on the single models. We also used Transformer LM for 2-pass rescoring. The Transformer LM contains 12 blocks with 16 heads, and the dimension of attention and the feed-forward layer was set to 512 and 2048, respectively. In Model 6, a 4-gram language model was joined, and the model achieved a WER of 27.6%. The output 100 best of Model 5 was further rescored using Transformer LM and gave 0.8% reduction in WER. Finally, our ASR system reduces the word error rate by about 48% relatively in comparison with the baseline. Final part, conclusions. In this paper, we presented TAL's ASR system for the task of the non-native German children's speech. We focused on applying a self-supervised based approach. Compared to supervised training, the self-supervised based model achieved better results in this limited training data task. We employ the 11-fold data augmentation, data cleanup, and semi-supervised VAD to improve the ASR performance. A 4-gram language model with CTC beam search estimated from children's transcribed speech was used for the decoding step, and the final step was performed by rescoring 100 best using Transformer LM. Our best submitted systems rank in the first place for the German closed and open track. Thanks for your attention.